n is equal to 10. It's like 1 by 10. What is the value of 1 by 10? Yeah?
0.1.
Maybe I'll write 1 by n. So it is 0.1. So 1 by 1000. Yeah?
0.001.
Okay. So you see the value is going closer to 0 as n increases. So this is what we call it as limit, right? So if an has limit, then the sequence an is said to converge, said to be a convergent sequence. Otherwise, it is said to be divergent. For example, here if you take an to be 1 by n, we say that it converges to 0. Okay. Now some rules to find limits here. So let an converge to, let's suppose an is converging to a and bn is converging to b. Then for addition, you have this compatibility, an plus bn converges to a plus b. And if you are multiplying with a scalar or doing subtraction, and so many other rules are there. So these rules are going to help us to solve problems. Okay, good. So we'll try to look at the first problem and we'll explore what can be done. So now we are looking at which of the following options are true. All are involving limit of some. Here you see either you have polynomial, just a polynomial, or polynomial both in the numerator and denominator. So only this form is involved in this problem, right? So here if the function is of the form f of x by g of x. So like this, okay? And suppose g of x goes to 0 as x goes to a. Okay. So for example, you take in this case, when you substitute, so let's say that this is your f of x and this is your g of x. Okay. So what happens to g of minus 1?
G of minus 1 is 1 minus 3 plus 2. It is 0, ma'am.
Yeah. So you see
0.
it's
0. It's not defined.
Yeah. So you see that g of x goes to 0. So here g of x goes to 0 as x goes to minus 1. So in this case, okay, if possible, we try to cancel the factor x minus a from both f of x and g of x. And then we try to evaluate the function at x is equal to a. Okay, so we have to see whether there are any common factors like x of a. So in this case, what is your a? What is your a in this case?
-1.
Yes, so a is minus 1. So what are we looking for? The common factor is x minus a. So we are checking whether x plus 1. So if it is x minus a, then this becomes x plus 1, right? So what are we checking? Check is x plus 1, which is actually if x plus 1 is here what? X minus a, right? X minus a is a common factor for both f and g. What do you think? Is it a common factor? Try to
Yes,
split
ma'am.
it. Okay, so how can you split the numerator f of x first of all?
X minus 7 and x plus 1.
Okay, x minus 7 and x plus 1. Good. What about the denominator?
X plus 2 and x plus 1.
X plus 2 and x plus 1. Okay, so we can split it in this way, and hence now what's the next step? Once you cancel and the factor with x minus a, we can cancel these. Okay, we can cancel these common terms, and then the limit is limit x goes to 1, x minus 7, x plus 2. Now you see that the denominator, if I'm approaching to minus 1, this denominator is not going to 0. And hence now I can directly apply the limit. So if I directly apply the limit, what is my answer?
It's -8.
-8.
-4.
-8.
7
-8.
and then here -1 plus 2. So it is
-1. -8.
Yeah. So you see the answer is -8 and that is the given value of this limit. So this is correct. Okay. So now can we try the same for this? Everyone try for this one. So already we factored the numerator and denominator. The same is given. Oh, why? Okay, now
X tends
here
to 0.
x goes to 0. Now are we in a scenario where the denominator goes to 0?
Limit x tends to 0. Directly we can apply in that simplified fraction, madam. Already we had the simplified fraction.
Yeah. So now my question is, first of all, do we have this kind of a problem? Whether the denominator goes to 0. Only then we have to factor. Otherwise, we don't have to factor.
No, ma'am. It's not clear.
No,
There is
ma'am, will not be
oh,
0.
okay. So in that case, can we straight away apply the value of 0 to all the x's here?
That is 2. 2 and
So if you apply
minus
what is
7
the
by 2.
numerator and denominator?
It's minus 7 by 2.
Minus
Minus
7.
7 by 2.
So is this option correct?
No.
Okay. So here
No.
you minus 7 by 2 and that's not -8. So this is incorrect. Okay. Now this is again a polynomial. For polynomials, you can straight away apply the limit again. So apply this limit and see whether you are getting this answer.
Yes, it is correct.
Okay.
It's correct.
So you see that here you have 2 cube plus 4 into 2 square minus 6 into 2 minus 7. So what is 2 cube?
It's 8 plus 16 minus 12 minus 7.
8.
8 plus 16
16.
minus
16
12
Minus
minus
12
12.
minus 7.
Yeah. So you have 24 minus 19, which is 5. So this is correct.
Wow.
Okay. Now look at this. Again, you have a scenario where you have f of x and g of x. Are we in this case or not? So when x goes to 3, what happens to the denominator?
It's
It
0.
goes
Not defined.
So this goes to 0 as x goes to 3. So in that case, we have to try to look for a factor like this. So can we do factorization here also?
X minus 3 is
X minus 3 whole square.
Yeah, the numerator is x minus 3 whole square.
Whole square.
So if we
So this is
cancel
x
x
minus
minus
3.
3, x minus 3, what will be remaining?
X minus 3 only.
Yeah, only x
3.
minus 3, right? So you have x minus 3 whole square on the numerator and x minus 3 in the
3
denominator.
minus 3.
So if you
Limit
can
0.
the term, yeah, so the limit is 0.
0.
So here it is given as 1. So this is also incorrect.
Ma'am, suppose the numerator does not have the factor of the denominator and it is not getting cancelled, then
Then it will, then the limit will not exist. Okay. Maybe we can try for L'Hopital. And if L'Hopital also does not help, then we have to say the limit may not exist. And we have to see whether there is another way to check whether such a limit does not exist. So if possible, we will maybe try to look for such an example maybe at the end of the session if we have time. Okay. All right.
What does a function mean when it does not have a limit, ma'am?
Okay, what does it mean if a function does not have a limit? So for example, let us take this function 1 by x itself. Okay, so 1 by x, how does the graph look like? The graph of 1 by x. Where shall I draw? Maybe here. Okay, so graph of 1 by x. So what happens as x goes very close to 0? So we already saw what happens. It goes very close to infinity, right? At 1, it is 1, right? Let's say this is 1. Okay. And then again, as x increases also here. Somehow it is like this, right? 1 by x, right? So now you see that here what happens as x goes to 0, the value is going towards infinity.
Infinity.
It is not approaching any fixed number. So in that case, we say that the limit does not exist. So this is one scenario. The other scenario is that we have to look at what are called step functions. So let us say you have a function like this, where I don't want to use the same color, maybe. So let us say you have a function, let's say this is 1, and I have a function like this. This is 1, this is 1. Okay. And then you have a 2, it's like this. Okay. So it means that the function is actually f of x is equal to 1 if x less equal to 1 and 2 if x greater than 2. This is the function. Okay. Now what happens as x goes towards 1? So you see that if I'm coming from this side, then I'm approaching which point?
Towards 1.
Yes. But if I'm coming from the right side, where am I approaching?
That's also towards 1.
If see, you have to be very careful. When I'm approaching this graph, the graph line is here towards 1. Which point am I approaching?
Towards 1.
1.
1, right? Now, if I am approaching 1 along this, what is the value I am approaching?
2.
2.
The y-intercept.
1.
So, as x goes to 1 from right, f approaches
1.
1.
1.
And x goes to 1, sorry, from
Ma'am, from left. From
Yeah, sorry.
left.
So from left, and here from right, f approaches
2.
2.
So if from left and right, if f is approaching a different values, it means they are not approaching the same values. So in this case also, we can say the limit does not exist. Okay. And there is some other scenario. Yeah.
Ma'am, for the left case, that the graph, can we also do it by like, how did you do it? Like the limit does not exist. Like, can we also do it like the way you do it, approaching from right and left in
This is
this?
different. That's what I'm saying. That's why I'm giving two different examples. Here, this scenario is different. This scenario limit cannot exist for two different reasons. Here, the reason is different, and here, the reason is different. Here, the reason is that x is not approaching any fixed value, but it is just going towards infinity. The value of x is just going up. Okay? Fine? Is that clear?
Yes.
Yes, ma'am.
Okay. Shall we move on?
Ma'am,
Ma'am,
this
whenever
right
there is
side
an asymptote,
function. Hello?
so
Sorry?
ma'am, whenever there is an asymptote, we can say that the limit does not exist in a way.
Kind of. So that is one case. As I told you, the asymptote case is this one. The other case is this. Okay? Fine? Okay. Good. So even if the function, suppose, is not defined also, the limit can still exist. So the value of the function, whether it is defined or not, is different from whether the function limit exists or not. So these two are different. So that you should be able to understand. So for example, suppose you have some function where, so you have something like a punctured function. So something like this, for example, let us say. Okay, some function. So let's say when retrieving data, suppose at one point suddenly you able to take the data. So in that case, so only at that point, I don't know what was the value, and then immediately write back, let's say there was a power issue sometime when I was taking this data. So at least only at this point, I could not see what was the data. But then after that, I know what was going on. So let us say this is your f. So your f is not defined at A. You don't know what is the value of f at a. Okay, so it is not defined. But what is limit x going to a f of x? So where is the function approaching when it is moving towards this point, towards a, either from the left or from the right? Where is it approaching? Let's call this point maybe L. Where is this point approaching?
Towards A.
Towards L, right? So it means that limit can exist even if the function is not defined at certain points. Okay, fine. Okay. So in fact, so this function is
It was
also
approaching towards A, na?
A, madam. In this
it's
particular
not
graph,
A. It's not A. See, as x goes to A, where f, the value of f you have to see. Value
Acha,
of f
F.
is on the
Okay.
y-axis.
FF. Yes.
So this is the scenario which is happening in these two cases. If you draw the graph, so this is actually x minus 3 whole squared. What does mean by x minus 3 whole squared? So if it is x minus 3 whole squared, but here when x is equal to 3, is this function defined?
no.
Okay, so in that case, how will the graph of this function look like? Can anyone first imagine and then I will draw? Just take few minutes to figure out how does it look and then I can draw and show you maybe.
The numerator will be a parabola.
Yeah, but
Whereas like
here you have to look it as an entry function, not numerator and denominator separately.
Ma'am, would it be a straight line function?
No.
A constant function?
it would be remaining by x minus 3 only. So it would
It's
Maybe
be
it's a
actually a
constant
straight
function.
line. Someone said straight line, which is almost correct, but just a small modification.
Ma'am,
minus
actually, it
3
would
would
be a
be
straight
intercept.
line, but ma'am, it would be a straight line, but at the point 3, at x is equal to 3, there would be like a kind of a hole, kind of a
Exactly.
0.
There will be break.
Yes, exactly. That is the scenario happening here. So here you see that. So x is equal to 3. So let's say that this is your 3, let's say. So somewhere below also here it will meet at 3. So the line is something like this. But here what happens at 3, your function will not be defined. So it is a scenario like this. Your function is not defined at x is equal to 3, but still the limit exists in this case. Okay, it's the limit here is actually 0. Okay, not 1. The limit exists in this case, but the function is not defined at x is equal to 3. Okay.
Means at 3 the fx is 0. That's it.
No. The limit, we are talking about the limit. Limit is different from the function value. Okay.
Okay.
Fine. Okay, good. Okay. So now we are moving to next question here. So which again involves limit and two other concepts. One is tangent and another is monotonically increasing and decreasing. Okay. So here now we are having a graph of some periodic function given here. Okay. So now for this graph, what are they saying? The limit of the function as x tends to 0 is 1. Okay. So this is the graph. Okay. When it is tending to 0, what's happening? So when this, look at the flow of this graph. When it is going closer to 0, where is it going? So we are trying to move towards 0. So
It
where
was
is,
positive.
so what is the
It is
value
increasing.
on y-axis? What is the value on y-axis? Y-axis
0 only.
it is approaching 0. So look at option 1 and option 2 and think and tell me. Don't answer immediately. Think and tell me to which point is it approaching.
It's
0.
0 only.
Approaching to 0 only.
So
0,
in
ma'am,
that
0.
case, what happens to option 3 obviously?
Option 1 get wrong and
Option 3?
No, it's defined. No?
Option 3 is also eliminated.
Yes. Okay. So in this case, we can clearly see that limit x goes to 0, f of x is equal to 0. Okay. Fine. All right. The next question here is about the tangent and also unique tangent. Of course, tangent means unique only. There is a unique tangent at the point x is equal to pi, but not at x is equal to minus pi. So we are looking at tangents of 2 points. One is at x is equal to pi and another is at x is equal to minus pi. Okay. So how does the tangent look like?
A straight line towards the point.
Here the x-axis itself is the
Horizontal
tangent.
lines.
Yes. So these are the tangents, right? So they are like along the x-axis in fact, right? So do we see tangents at these 2 points or not?
If we consider
They are
the
same.
axis,
Yes,
then we
ma'am.
have the tangent.
Yeah, we have tangents. So in that case, look at option 4 and 5, think and then answer. Which one is correct?
Option 5.
Option
Option 5.
5.
Option 4, ma'am. There is a
Option
unique
5 is
tangent at the
correct.
point x is equal to 5, but not at x is equal to minus 5.
Okay,
Ma'am,
why?
what does it mean by
The
unique?
option 5.
Option 5 is correct.
Ma'am, I
Okay.
think option 4 is correct.
Okay,
Option
okay.
4 is correct.
Ma'am,
Okay,
ma'am, option
hold on.
4 is correct, 5 is
Okay,
wrong.
okay, whoever is saying, okay, hold on. So those who are saying option 4, can you justify why at x is equal to minus pi there is no tangent?
There is
Ma'am,
a
there is a
tangent.
tangent, but it's
There
not
is
a
a
unique
tangent, but
tangent.
same, madam. It's not unique. For both of them, the same tangent.
Okay. So
Actually,
Yes,
ma'am,
ma'am,
in the
same
option,
reason.
it is saying that it is unique tangent, but for both of them, it is same. So,
no. Here they are saying about the tangent. You have a tangent at a point x is equal to pi as well as x is equal to minus pi. I guess there is a confusion in this case. Again, read the statement carefully. Read the statement carefully.
Well, if we consider the tangent at x to x at pi is unique, then automatically x at minus pi will become not unique to a man. So option 4 is correct.
So what you are saying is that both are having the same line as the tangent, right?
Yes, ma'am. Yes, ma'am.
But
Yes, ma'am. Yes.
is that what they are meaning here?
Yeah, the fourth one is meaning the same, ma'am.
See,
It is
here,
not having a separate tangents. It is not unique tangents maintaining at both the points. It is the same tangent.
hold on. I guess there is a problem with the understanding of the question. What they are saying as uniqueness here is that, so here at x is equal to pi, the tangent here is just only one line and there cannot be something, for example, in the, actually, this statement could have been written better. I agree with that. Because here unnecessarily this word unique is creating this confusion. Either they should have said that there is the tangent for x is equal to pi and x is equal to minus pi is same. Either that or the tangents for x is equal to pi and x equal to minus pi are different. They could have given it in that way. But here they have used the word unique and it's creating confusion. I understand very clearly why you people are confused. But here what they are trying to say is that they are saying that at this point you have only one tangent and not more than this. So, and it is obvious that the tangent is of course always unique. So for example, if you have some sharp edge like this, then you know that you will be able to draw two lines, something like this for this point. That's why we say that the tangent at this point does not exist in fact, right? So here I guess this uniqueness, the word unique is kind of confusing. So there is a tangent at x is equal to pi as well as x is equal to minus pi.
yes, ma'am, because unique, there is in both the
Just
options.
one
So
tangent
we
is
have to
what they are
consider
saying.
unique.
Okay, but
So, ma'am,
definitely
basically, this unique tangent point
What
was
is the
talking
answer,
about
ma'am?
having a kink. When we have a kink, we don't have a unique tangent. Is that right?
tangent means it is always unique only. Why specifically they use this word here? I seriously feel that it's kind of misleading the
Yes,
question.
ma'am. Ma'am,
Because
but we have
here
to
we are in a scenario where both these points are having the same tangent. So the word unique is kind of confusing and leading us to think it as the same tangent for these 2 points, right?
Ma'am, I guess
But
they
then
are
ma'am,
saying
even
that
when we
if it
go
is
by the definition that you gave for unique tangents, that
Yeah. So in that case, you see that at each point we have a
like in a modulus function, we won't
yeah.
be having a unique tangent because then we'll be having two lines.
So in this case, we don't have such scenario. We have a unique tangent for both x equal to minus pi and x is equal to pi. Okay.
ma'am, I think it is a part of a practice assignment where it is shown that the option 4 is correct, but option 5 is wrong. So,
Yes, ma'am.
Okay, so I guess
yes,
this
ma'am,
statement is
because
kind of okay. So let's not go with these options. What is the meaning? So let's be clear with that. So here, the tangent at x is equal to pi and x is equal to minus pi is given by, can you say given by, what is the equation of the tangent in this
A
case?
is equals to 0.
X is equal to 0, right? So this x-axis is the tangent. So the tangent is the same at x is equal to pi and x is
Then
equal to...
y is equals to 0.
Oh, sorry, yeah. Y is equal to 0, sorry. Given by y is equal to 0, the x-axis, right? So in that case, so this is the meaning here. Maybe, yeah, so if they are meaning that the tangent at x equal to pi and x is equal to mine, in that case, why they are saying but not at x is equal to minus pi? This is really confusing for me. I feel that this is the correct option. For me, if I read this, I will say that this is the correct option, understanding this.
Yes, ma'am. Option 5 is correct.
Yeah, understanding this and this is what I will
ma'am, I guess
consider.
they are saying that the unique tangent is not like at x is equal to pi and x is equal to minus pi, there is a common tangent. It's not unique. If we think by that way, na.
See, if it is common, then they would have not written it in this way, right? They would say that the tangent at x is equal to pi and x is equal to minus pi, they are not same. They would have not written there is a tangent at x is equal to pi, but not at x is equal to minus pi. This is not the way you write for a common tangent. So I will say option 5 is correct. See, whoever is having confusion, don't worry about this. See, if you understand this much, then just move ahead. Okay, don't worry about it. Okay, both of these points are having tangent and then they are having the same tangent, but each of these points are having just unique tangents, that's all. Okay, if you understand this, just move ahead. So let's move to the next point, which is monotonically increasing. Okay, by the way, I will note that down that your PA is having the same question and you are given option 4 as the correct option. So
yes,
let me
ma'am.
note it down and discuss with the team and see whether we can restate the problem. Okay, because it's kind of misleading. All right. So here, option 6 and 7, it is talking about monotonically increasing and monotonically decreasing. So first, what is the definition of monotonically increasing and monotonically decreasing? Can anyone say?
Increasing in a
it is
gradual
always
manner.
increasing and always decreasing.
Yes, ma'am. Without any stop, it is increasing or
Increasing in a gradual manner, decreasing in a gradual manner.
So if x1 is less equal to x2, okay? And if f of x1 is also less than or equal to f of x2, then we say f is increasing, right?
Increasing.
And if f of x1 is greater than or equal to f of x2, in that case, okay, monotonically increasing. F is
Decreasing.
monotonically
Decreasing.
decreasing. Okay, the definition we have. Okay,
What
so now
does the word monotonical refer here?
repeatedly, you feel the subject is monotonic or you feel the week is monotonic, like it's kind of repeated pattern. So repeatedly again and again it's increasing.
Yeah, it's there, I think.
Yeah. Fine.
That
Ma'am, but
pattern.
monotonically increasing is not same as strictly increasing, na?
No, that is different. See, for example, if you consider any constant function, you can say it is monotonically increasing, but it is not strictly increasing, right? Okay.
Basically, not having a point of inflection would mean monotonically, but strictly has its own definition, which does not include the equal to sign.
Yes,
Ma'am,
yes.
can you just
Strictly you have,
explain it a little graphically?
okay. So
Strictly
for the,
monotonically.
yes, yeah. So suppose you have this function, let us say f of x is equal to some constant value. Okay, so
Continuously increasing is same.
so let's say f of x is equal to 2. Okay, so in that case, you can say that for x1 less equal to x2, your f of x1 is actually equal to f of x2. Okay, so you have values, a function like this. Or suppose you have another scenario where you have step functions also, or you can have functions like this also. Somewhere you have like this. Okay, so in this place, you see that within this range, you see that let's say some a and b. So for values within this, you see that the function is kind of having the same value, but otherwise it is kind of increasing. Okay, so this is monotonically increasing, but strictly increasing function. So if you are talking about strict function, then in that case, it's
Straight line with a positive positive slope.
yeah. So the slope is never 0. It's always having a positive slope. If it is
Ma'am, is
increasing.
the graph of root x is strictly increasing?
Root x.
Graph of root x, ma'am.
Yes, yes. Let's see.
It's
First,
strictly
let
increasing.
me. If you take any linear function, it will be either strictly monotonic or strictly monotonically increasing or monotonically decreasing. Okay. So this you can see. Now, what about root x? First of all, where is root x defined? What is the domain?
0 to infinity.
0 to infinity. In its domain, what do you think? Is it increasing or decreasing?
Increasing, but is it
Yeah.
monotonously increasing or
Yes.
strictly increasing?
So you can say, in fact, it is strictly increasing. Why? Can there be two values for which the square root is same?
No,
Because
ma'am.
considering
not
only,
possible.
that's why I asked the domain. You are looking only at x greater than 0. So in that case, what you are doing, you are looking at only values which are like constantly increasing and there is no equal to sign. In that case, it is strictly increasing, in fact. Okay. Okay,
And
fine.
ma'am, the graph that you draw of the straight line, this is also strictly increasing, na ma'am? Straight
This is,
line.
yeah,
The
this
black
one.
one, ma'am, just below.
Yes, yes.
This is
That's,
strictly increasing, na?
yeah, I wrote strict and draw this. Yes. Yeah. Okay, if you
Ma'am,
take, yes.
can we say that monotonically increasing functions have local maximum? Ma'am?
Local maximum in general, yes, it should have a local maximum. We can say, yes. But you can see that this is also, yeah, local maximum means if you are taking within a small interval, if this is the highest point, then we can say. But if you are considering the entire domain R, I don't think we can say, because strictly increasing function also falls under monotonically increasing function. So here, what is the local maximum throughout this? We cannot say that, right? So you have to be careful about what is the domain you are talking here. Okay. Okay, fine. So let's come back to the problem we are looking at. So the given function is monotonically increasing in the interval minus 0.5 and 0.55. Okay, so we are looking at these 2 points. Within this interval, what is happening? What is happening in this entire interval is what we are looking at. Not just these 2 points in this entire interval. What is happening to this
It is
function?
increasing and decreasing, ma'am.
Yes,
Either
the function
increasing
is first coming down
Increasing and going increasing.
and then again it's going up. So it is neither
Not decrease.
increasing nor decreasing in this interval. Okay. So
Someone please close their mic. I
yes,
guess it's Himanshu. Yeah.
Kindly mute yourself, guys.
too much disturbance. Yeah, thank you. All right, so we see that it is neither monotonically increasing nor decreasing. So both the options are incorrect.
Correct.
Okay. So because you see that it's first decreasing and then increasing, so it's not happening throughout this interval. Okay. So the last two option are, is it
If
clear for everyone?
if the question has stated from 0 to 0.5 pi, then it is strictly increasing.
Exactly.
Okay.
It can, ma'am, if the option would be monotonously increasing from 0 to 0.5 pi, then also it would be fine.
Sorry, what's the interval you are talking about?
0 to 0.5 pi.
Yeah, that's what the student.
Monotonously increasing, if it is saying
Yeah,
in the
yeah.
option.
Yeah. Then it will be monotonically increasing.
Uh,
See that 0 to 0.5, it's monotonically increasing, and minus 0.5, maybe, let me write 2, otherwise it's look like minus. So minus 0.55 to 0, it's monotonically decreasing.
so in this case, which is minus 0.05 pi to plus 0.05 pi, what you can say about this function? It is
I have already written. It's neither increasing nor decreasing.
okay.
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 Is it clear for everyone?
But actually, it's decreasing then increasing, no? If you
See,
can see, like,
when you are talking about in an interval, what is happening? Okay. So you can not say whether the entire interval. So if you are talking about increasing or decreasing, you are talking about whether you have the same pattern in the entire domain or not. So in this case, in the entire domain, do you observe this pattern? No. You observe this pattern? No. So neither of this pattern is there throughout this domain. That's all. Clear?
okay.
Fine. All
Yes.
right. So yeah, you see option 2 and option 5 here actually are given correct. But anyway, I'll check with the PA thing also. All right. So moving to question number.
Ma'am,
Yeah.
as we said that monotonously increasing, we can also
Hmm.
say that it's strictly increasing in a way.
Yeah,
So
yeah.
it's one and the same thing.
In this case, yes. It's not the same, but in this case, yeah, strictly increasing implies monotonically increasing, but not the other way around. So you have to be careful. They are not same. Okay.
Ma'am, if there would be a option where it is where they say that the function is increasing but not monotonically, so the term monotonically, what is the opposite word of it? Because maybe they can give the option for confusing us.
Such a confusing thing where you confuse the definition itself. I don't think you will be given. But anyway, there is nothing called opposite of monotonically increasing. First of all, monotonically increasing means that it is happening throughout the entire interval. Okay, so that is
Perfect,
what
ma'am.
I mean by monotonically increasing. And the other thing is about strictly increasing or decreasing. That's all. You don't have something like opposite of monotonically increasing. Okay, fine.
Ma'am,
Okay.
are functions without limits discontinuous functions, ma'am?
Yes. We
Okay,
can
ma'am.
say when you have no limit at certain points, then at those points we have discontinuity. I guess that is kind of the last topic of this week. So please hold on. Okay. Fine. Okay. So now we are looking at question 3. So you have, okay, 1, 2.
Where can I find this PDF?
Usually after my session, I usually share directly in the chat. Okay. At the end of the session, it will be shared in the chat.
Okay, ma'am. Okay.
Ma'am, do you also upload it on the dashboard on the PDF section also?
If you want, I can do that as well.
Yes,
Okay.
ma'am. It would be, yeah.
Oh, okay.
Yes, ma'am. Please
Ma'am, please
put it
upload
on.
it.
Yes, I'll do that. Okay, fine. Okay, so here we are having, so this is one function, this is one function, and yeah, you have 3 different functions for which we are looking at limit x goes to 0. Okay, and we are given that we can use these 3 limit rules in this case. So obviously in the first question, we may have to use both this, I guess. So look at this given function here and also look at this hints given to you and see what you can do to solve this and using this.
Option 1 is correct, I guess.
Okay, so how are you going to use this here?
Option 4 is
We
correct.
can divide by 1 so that we get the function.
Sorry, what?
We can split the like we can take log 1 plus x by 1 along with the limit so that we get it as 1.
So let me give
And
a
again,
hint. You can multiply and divide by certain things so that this will look something like this
Yeah,
and
we
this.
can multiply and divide by x also
yeah,
directly. So become 2.
x we can do.
Yeah. Okay, let's try to do that. So the first one, so you have limit x goes to 0 log of 1 plus x by sin x. So let's multiply and divide. If I
Yes.
need it in the denominator, so let me multiply and divide by 1 by x. So then I have limit x goes to 0 log 1 plus x by x and limit x goes to 0 log, sin x by x. Now what's the limit of the numerator? 1. And the limit of the denominator?
1.
1.
1.
Okay, and then you have a 2 here, and so you will get 2 into 1, which is 2. Is this fine?
Yes,
Okay.
Yes, ma'am.
Okay.
And can we also write sin x as x minus 1 and log 1 plus x as also x minus 1?
Why?
And from the formula, we can interchange it and we get the same answer, one moment.
Why you have to interchange that? I don't understand.
So, ma'am, from the formula, sin x by x equals to 1, we can move the x to the right side and get the same answer, ma'am.
I don't understand where you are moving the x. You are saying you want to split this?
No, ma'am, in the given formula, 3, some more things, S1, then
Here.
you can move the x to the right side.
No, you cannot do that. See, this is one function together. Okay, this is one function f of x. So here they are saying limit x goes to 0, f of x is equal to 1. Okay, you cannot take this x here commonly because here this x is within this. It's not something like outside the limit. No. If it's just a number, then yes, you can do that. But here it's x. Okay, fine. Okay, so the next question here is, so the next one is here about
Ma'am,
sin.
we can't do it because there is limit, na ma'am. We cannot do like, we cannot go to the other, like x cannot go and multiply 1 because there is a limit.
Exactly, that's what I was saying, yes. Okay, so now here you have this function as your f. How are you going to make it look like this? See, there is one thing I will ask you. First, tell me whether it is correct or not. Can you tell what is limit y goes to 0 sin y by y? What is the limit?
It's 1.
1.
It's 1, right?
It's 1.
Just because I'm changing the variable, nothing is going to change. So only the variable I'm changing. So now with this hint, can you think of a way to solve this using this?
We can divide and multiply with
We can
3.
multiply and divide with
Divide and multiply by what?
3.
3.
By 3.
Yes.
Okay,
Yes,
so let's do that. So
Then if we divide by 3, we will get 1, I think.
Sine of 3x by 3x
3x.
into 3.
3.
Okay.
This
So now, what do you know about this part?
this
So
will become 1, then it will become as 3.
yes, yes. So now limit x goes to 0. This part, you know, it is 1. So you will get 1. And this is just a number. So it will remain as it is. So your answer should be 3.
3.
Yeah? Is that fine?
Yes, ma'am.
Okay. So in that case, now you can tell me the answer for option 5. What should be the answer for option 5?
It would be 5, I guess.
Yes, it should be 5.
5, it
Should be 5. Right? Okay. So the next question here is like combining this and this now. So you have to use some similar trick we used here. So first think and then tell me what is that we need to do.
Ma'am, multiply and divide by x by 4.
and then multiply by 5 so that the sin x is also neutral.
Okay, so step by step.
Yeah.
Numerator.
Ma'am, 1 by 25 is the answer, I think.
Okay, so
Ma'am,
let's.
we have to multiply x by 5.
Okay, so you have to multiply and divide this by x by 5. Okay, then what?
Then again multiply divide by 5x for the sine 5x to get to 1.
So you want to multiply and divide by a 5 here again.
Yes. Yes.
Okay.
Yes, ma'am.
So in that case, what is that you are getting? So here
You are
sine
getting
5.
full 1.
Yes, yes. So here you have sine 5x and then you have here 5x. So this part you will get 1. And what is the numerator again? Limit x goes to 0.
1, yes, 1 by 25 is
1.
coming.
The numerator is again 1, right? Okay. So then what is the final answer here?
1 by 25.
1 by 25.
1 by 25. So here you have 5 here and 5 here. So you have 1 by 25. Okay. So here.
It is correct.
Sorry, this is incorrect. This is incorrect. Correct. Correct. Okay. Oh, sorry. Last one is incorrect.
Can you just once again explain option 8?
Yes. So I guess the detailed solution is, oh, it's not given. Okay, let me write it again. So maybe here itself, I'll try to explain. So here, what is given to you? E power x by 5 by minus 1. So this is the numerator. So I'm multiplying and dividing it by x by 5. So you have divided by sine 5x. I'm multiplying and dividing it by x by 5. Okay. And then also in this part, actually here you have, if you have y and y, then only you can apply the limit. Here you have sine 5x. So what is that you need here? What is that you need here?
5.
5. So again here I am going to multiply and divide by 5. Okay. So here what will you have? So here you will actually have e power x by 5 minus 1 by x by 5. Okay, so here actually 1 by x by 5, multiplying and dividing by 1 by x by 5. So I missed that 1 by x by 5. Maybe I'll put something like this. Maybe more clearly I'll write. Should not be confusing. 1 by x by 5.
How 1?
X by 5. Okay, because I'm dividing by x by 5 in the numerator as well as denominator. So this is what is happening. Right? Correct? Yeah. Now you see that as limit x goes to 0, this part goes to 1. Already this part is going to 1 because of this. Right? This is y, this is y. So x by 5, x by 5. I can put it as y, and you know that as x goes to 0, your y goes to 0 as well.
No,
So
I
this
think you are missing -1.
Sorry, what?
1.
Yes.
By dividing 1 divided by x by 5.
Tanmay, please mute yourself.
1 divided by?
X by 5.
Yes.
Here you are missing minus 5, I think. Or I am not getting how dividing by 1 by x by 5.
You are not understanding which part? How I'm dividing x by 5 to the numerator?
How you are dividing x by 5 by 1? Both numerator and denominator. 1 and the part 1, where did you get that? Can you just explain?
Okay, see here, what is that I need? What is that I need?
I'm missing something.
Here, you see that what I want is, I have e power y minus 1. Let me write here. E power y minus 1 by sine z. This is what I'm having. Okay. What I want is that I want e power y minus 1 by y and sine z by z. This is what I want. So sine z by z. This is what I want. Okay.
This is the formula.
Yeah, only then I can apply this formula. Yeah. Yeah. So now in this case, my y is x by 5 in the numerator. Correct? So that's why instead of this y, I have 1 x by 5.
Okay, I'm missing the formula. Okay.
Okay, got it? Same way we are doing for the denominator, but the denominator, yeah, I'm not obtaining z straight away by doing this x by 5. What I need is actually 5x, not just x. So again, I'm multiplying and dividing with 5. Okay?
Okay.
So then
multiplying and divided by 5x, not 5.
5 only, not 5x. Already I have x.
So it becomes 5x by 5.
Yeah, sine 5x, and then you have already x by 5. So I'm just multiplying and dividing by 5 only, not 5x.
We want 5 by 5x.
Yeah, so here you are having 5 and then 5 here. And so you see that here you are having in the numerator, this is 1, and here you have 25.
25x by 5x by 5.
So 1 by 25. Is that clear?
Yes, ma'am.
Okay, fine.
The 3 identities which you have in the left hand side, are these the formula which we have to remember?
Yes, yes. Okay, so these are formulas which you have to remember.
So kind of solution for all the options.
Okay, good. Okay. What's this? So this and these are different. This slide was some pre-prepared slides. You see the question is like 3, 5 here, and here it's 7, something different. But anyway, we know what's the answer, right? So we know that, yeah, this is the answer, this is correct answer, and this is correct answer. So it's fine. Okay, fine, no problem. So now we are having, so we know these 2 formulas already. So we have now 2 more formulas to remember. Okay. So now we have to use these 2 formulas as well to solve this. This is like a really problem which you cannot solve it on the flow. I will say that I will definitely say that unless you try enough problems in limit, this is not a problem you can do it in the first shot. Okay, so you need to.
Ma'am, these 2 formulas, these 2 extra formulas under root 2 by x, we have to remember these 2 also. It looks quite complicated. The lower 2 formulas.
Yes, we need to remember.
It looks quite heavy actually.
Yeah. See, I'll just, I understand the difficulty. When you people are doing math, how many math papers in one term are you doing?
1.
1.
Yeah, 1.
Okay, so for math majors, we are doing all math papers in one term. So how many formulas are we remembering? Okay, so this is not a big deal. You can definitely do it. Okay, so don't think it is a big deal. I understand there is some work involved, but just put enough effort, you will definitely able to remember. Okay, it's not a big deal. All right, so yeah, so this, as I told you, this involves quite some steps here. So let's go step by step. Let's not just jump into the solving the entire thing. So how will you solve this part? First, look at this part, which is familiar to you. How will you solve this part?
Ma'am, we can use
divide by
Divide or
we can
multiply by
divide by
6 by n.
we can
Okay. So once you
Ma'am,
divide by n, then what can you do?
ma'am, I think first we need to take the limit inside both the two terms.
Yeah, step by step we'll do. So first thing is that we know this part is kind of easier for us to do. So for this part, what will we be doing? So what we will do is that we will do like this, right? So you multiply and divide by 6 by n, right? Now what will happen to this part?
It will become 1.
It gets 1.
So this part, you know that this will go to 1. This is as x goes to. So you know that this is only when x goes to 0. But here you are having 6 by n. Are they equivalent or different? You have to be careful. So here n goes to infinity. As n goes to infinity, what happens to 1 by n?
It goes to 0.
0.
Okay. So then in that case, this 6 by n is going to 0. So can we apply this formula now? As n goes to
Yes,
infinity,
ma'am.
can we say that this value will go to 1? Yeah? Is that fine?
Yes, ma'am.
Okay, so we are having an idea how to deal with the first part. What about the numerator of the second part?
Divide by
Ma'am, we
1
can
by
multiply
n.
1 by n.
Yes,
Multiply and divide by.
exactly. We can
And
multiply and divide by 1 by n. So e power 1 by n minus 1 by 1 by n. Okay. So in the numerator, you are having 1 by n. Again, the same logic will apply. As n goes to infinity, this will go to 0 and hence this formula will also work. And you have 1 by n again here. So here again, you know that this part will go to 1. Okay. What is there in the denominator? What is there in the
Convert
denominator?
into e. It's also divided by 1 by n.
So you have to divide by 1 by n, or see here you have power 1 by x commonly. Remember that.
Yes, ma'am.
So
n factorial to the power 1 by n.
you need an x here and you also need x factorial power 1 by x. So how are we going to deal this? Two things are needed. You only have square root of 2 pi x power 1 by x. So these two parts are needed. So what are the things to be done for this part?
We can divide and multiply by factorial n, and from that the upper factorial n we can take n, and then we
So
can
remember
take
the
n
power
minus
is
1.
not x, it is 1 by x.
Ma'am, we can use the fourth formula x upon root of x factorial x kind of.
But
Instead
here,
of x
how
we
are you
have
going to
n
deal
here.
with it?
Instead of
But
x
how
we
are you
have
going
n
to
here.
deal with it?
Okay.
Ma'am, we can simply multiply and divide by n. Then it's all.
How it will work? You want these things. Just multiply and divide by
Ma'am,
whatever is missing, right? Why are you
Multiply and divide by n factorial to the power 1 by n.
and
Yeah.
Instead of x we have n here. So
yeah. So what are the things missing? What is that you need to multiply and divide?
factorial n.
n factorial to the power 1 by n.
And Yes, that is
And n as well.
exactly. Exactly. See, what is that the formula is limit. Let me write everything in terms of n so that it's easier for us to visualize. Okay. So what is that we already have? We already have square root of 2n pi power 1 by n. This is what we are having. Okay. And what we need is, we need n, and we also need n factorial power 1 by n. This is what we need. Okay. And this we know that is equal to e. Now is it very easily visible that what is that we need to multiply and divide? Yeah.
Factorial n to the power 1 by n.
Yeah.
Yes, ma'am.
N into square root of 2n pi whole power 1 by n by n factorial power 1 by n. Here I have n factorial power 1 by n by n. Does it make sense? Yes or no? I'm multiplying and dividing.
Yes, ma'am. It
And
makes
n
sense.
factorial power 1 by n. Okay. Now you know that this part is going to what value?
E. E.
Okay, as n goes to infinity, this part goes to e. Okay. Now what about this part? You have here x by n square root of n factorial. But here, remember, you have something else. So some simplification has to be needed, and then we can apply this formula. So first these things we will put, and then we will see how does the simplification work. So we have an idea to start with. So this is how in exam also, if you are given some problem like this, don't go do everything at a stretch, do step by step. Okay. And then when you have an idea, then try to put everything together. Okay. So now you see that you have
Ma'am, I have
limit.
this one doubt.
Yes.
When you were explaining this thing above a little bit,
Hmm.
and here it is n goes to infinity, and there is x. This one, yes, ma'am.
Yeah.
Yeah, ma'am. What is its application here in the question?
So the question here is, they are saying limit n goes to infinity. But the formula for these two are in terms of x goes to infinity. So how are we going to apply this formula to this problem? Because the problem is about n goes to infinity, not going to 0. Can we still apply this? Yes, we can apply, because instead of x, I'm having here 1 by n, and this n goes to infinity is same as 1 by n going to 0. So my x is 1 by n. And it goes to 0. So this formula,
We basically reciprocate
we are saying
So
that
ma'am,
I'm
you
going
are
to
saying
take x
that we
is equal to
basically
1 by n.
reciprocate.
Okay. So and you know that this is already going to 0 only. Okay. Or in fact, I can put 6 by n also. Okay. Clear?
So you basically reciprocate.
I cannot hear you properly. Sorry.
Reciprocate n and infinity 1 upon n in that winner.
Exactly. Yeah. So as n goes to infinity, this here, what is that we are having? We are having 6 by n. So we are looking at what is happening to 6 by n. 6 by n goes to 0. And in place of x, this 6 by n is what is there. That's why we are concerned about this. Okay. Got it? Okay. It's not just blindly we are reciprocating, because this is what is present in place of x. That's why we are able to apply this. Okay, fine. So you see that we are first multiplying and dividing by 6 by n. That was our first plan. And then we are multiplying and dividing by 1 by n, the numerator, the next thing. And then in the denominator, we are multiplying and dividing with n and n factorial power 1 by n. So this is the first step we planned. Yes, we have did that. And then we are trying to like rearrange things by pulling this inside. We are now going to bring this square root of n factorial or 1 by n. So inside. Okay. Now nth root of n factorial, I'm bringing inside. So once I'm bringing inside here, So instead of writing it then in the numerator, I'm going to write it here, which is equivalent, right? So I'm going to write it here. And then when it comes here, what happens to, this is for the first term. And what happens to the second term? In the second term, now you have already, here you have n factorial power 1 by n, which is, see, remember this is first of all same, that n factorial power 1 by n, it is same as nth root of n factorial. First, this we should make clear. So you know that this is same as this. Okay. So now you see that when I'm multiplying this here, this and this are going to get cancelled because we are having the same terms. Only now in this place we are having, so we can make use of this formula in this place. So now this value, we know that this goes to E as n goes to infinite. So now we have formula to apply in all places. So just plug in those formulas. And what is remaining? So this goes to 1, this is 6, and this goes to E. And this is 1, and this is E. So you have this E times of 6 by E minus 1 by E. So E gets cancelled. So you just have 6 minus 1, which is 5. Is this clear? Whether all the steps are clear for everyone?
Yes, ma'am.
Okay. Fine. All right. Shall we proceed? Okay.
Yes, ma'am. Yes.
And we have to do this in examination hall.
If you have such a question, yes. Okay. Fine. All right. Suppose a company runs 3 algorithms. This I'm going to give you completely give it to you because this is a very simple one compared to what we have done so far. I recommend you all to read it yourself. I'll give you 10 minutes time. In this 10 minutes, please don't tell what your answer is because let the others also have some time to think on their own. So please, it's a request to everyone. If you have completed the answer, please wait. Let the others also get some time to think. Okay, take 10 minutes. Everyone try to solve this question completely by yourself. If not, I will help you after 10 minutes. Put your effort. Make use of the time.
Ma'am, option 1 and last two options are the correct ones.
Hold on. Let us give time for others.
Okay, ma'am. Ma'am, at the end of the session, I actually have one doubt. If you can address it at the end.
Okay, fine. Okay, so we'll discuss your doubt at the end. Now, can you all see, tell me what is the status of the problem, how far you have completed?
Yes, ma'am, it's
145.
finished, ma'am.
Okay, good. So, what are the correct options?
145.
First and last two.
145. 145.
1, 4, and
1,
5.
2, 5.
4 and 5. Okay.
1, 2, 4, 5.
Okay, good. So your answers are correct only. So let's just re-verify your answers. So the first one is very straightforward. How do you deal with the first one?
We can ignore the 5n and this one n square by 6n square as limit tends to infinity.
So you divide, actually here in this case, you divide the numerator and denominator by
N square.
n square, right? So if you divide the numerator and denominator by n square, then what will you have? You will have something like this. 1 plus 5 by n and 6 plus 1 by n. So as n goes to infinity, this part goes to 0, right? So this part goes to 0 as n tends to infinity. So you simply have 1 by x. So this is the value. So this option is correct. Okay. And for the second part, so this is just a number. So what about this function minus 1 by n power 1 by n? Minus 1 power n.
And both tends to 0. So you have to consider
As
one.
n goes to
It will be
infinity.
0, ma'am.
Okay. As n goes to infinity, this value goes to
0.
0. right? Hence, you see that the answer is 1 by 8, which is 0.125. So this is also correct. What about the third one?
It will be very big value in the denominator.
So yeah, so as n goes to infinity, here you have something undefined. So you have to multiply and divide by
e power n.
e power n. So e power n, if you multiply and divide, you will have something like this. And here, as n goes to infinity, this whole thing goes to 0. And hence you have 1 by 7, which is 0.142. So which one is the maximum? So this is the maximum. This is the minimum, right? So algorithm 1 gives you the maximum error. And the minimum error is given by algorithm 2. Yeah? Yeah, tell me. Okay. So now
But
both,
why we are making limits n to infinity and why not n to 0 and tends to 0? Like, what is the reason for that?
They are given as n tends to infinity.
Question. Okay. Fine. Okay. So you are asking in the question itself, why are they giving like this, or?
In the question only, I was asking why is particularly.
Okay. Because here, see, the question is about the error estimation on the number of available data. So here, this n is representing the available number of data. So if we are looking at what happens to this error as the data number increases to very large, it means we are seeing what happens when this n blows up, that is n goes to infinity. You understand in the context now?
Yes, ma'am. As the data got increased, the
Yeah.
estimation got decreased in a way. Yeah.
Yeah. So as the data is increasing, so what happens to this error? So as n increases, what happens to this estimation? That's what we are looking at. Okay. So this is definitely incorrect. Okay. So this is clear for everyone, right? Okay.
Yes, ma'am.
Okay, fine. All right. So now, why I'm not able to open the other one? Maybe I have to stop sharing and then
Ma'am,
open.
just the last page. I want to take the screenshot for the revision, ma'am. Just yes, ma'am. This one. Thank you, ma'am.
Okay. So this is yeah, this is done. And let me stop and share again.
Ma'am, for some reason I missed the yesterday session. Where I can find it now?
Sorry, what? What you cannot find?
Actually, TA sessions recording is on the Google Sheets every day.
Okay. So yeah, we'll continue here. Okay. So what are functions of one variable? Here in this whole week, we are looking at functions of one variable, right? In math 2, when you move to math 2, you will be looking at functions of 2 or more variables. Okay. So here we are looking at functions of one variable. It means what? The domain is R. Okay. So it means you are looking at just one variable X. Okay. And we are looking at what is f of x. So these are functions of one variable, right? And how do the graphs looks like? The graph of a function in one variable is just any curve in the xy plane. So if you have something like this, and if you have this, so this is a function of one variable, right? Okay. So now here you see these are some examples of functions of one variable, right? So here you see all these are some familiar functions. So select which of the following are functions in one variable.
1 and 3, ma'am.
1 and 3. Because what is the domain for G? G is a function from, what is that you notice? R2 to R. So here this is not a function of one variable. Right? Okay. So we have already seen monotonically increasing and monotonically decreasing, right? So here we are looking at functions from R to R. Okay, so in this case, considering these as functions from R to R, okay, so which of these are monotonically increasing, you think? So already the answer is here. F of x is equal to x, f of x is equal to 2 power x, and f of x equal to x cube. These are monotonically increasing. But looking at the graph, y is equal to x power 4 also looks monotonically increasing. So where is the issue with y equal to x power 4?
Near the x-axis.
Yeah.
It is quite strictly increasing, like very much, I guess.
Don't just look at the graph, you will be misleaded. We are talking about domain R. We are looking for the here we are considering the domain R.
Till 5 of the domain, it's 0 in the range.
No, if you actually take Desmos and zoom it, it's not actually like equal. You can see that it will look something like this. Okay, if you zoom in, they are not equal, because now we have kind of
We can call it like a steep.
okay, maybe I'll straight away ask, what happens to x power 4 when x is less than 0?
It's still
It
positive.
is positive only, madam.
Is it increasing or decreasing?
It's increasing.
It's increasing,
Decreasing.
right?
Getting
The
positive value.
The graph looks like this for x power. Sorry, this is very bad. I'm not very good at drawing, but yeah. So this is something like this. Okay, your x power 4 will look something like this. Okay, so this is your 0. So what happens in this part? In this part, your x is, the function f is decreasing. And then it's increasing. Right? So that's why x power 4 is not monotonically increasing in R. If you are only talking about x greater than or equal to 0, then yes. If you are talking about whole R, then it's not monotonically increasing. Got it? Okay? Fine.
For x power 4, if we ask particularly, we have to specify like in the left direction it is decreasing and the right it is increasing.
See, it's not about left or right direction. Looking at all the points in R.
Overall, is it an increasing function or decreasing function, ma'am?
Yes, yes.
And same goes with x 5, x to the power 5 and 6.
Sorry, what happens? What are you talking about?
Same answer goes with x to the power 5 or 6.
Same answer goes to x square. Okay?
No, you just said x to the power 4 is not the increasing.
Yeah, x power 4 and x square. For both, the graph looks very similar to this, and hence they are not monotonically increasing.
Instead of x to the power 4, what we get? X to the power 5, 6, or something greater than that.
How does the function, what is the knowledge you need to answer this? If you, okay, one thing, if you know the graph, then you know the answer straight away. If you don't know the graph, then you just have to think about what happens in the negative part and what happens in the positive part. What do you think will happen to any x power n where n is even? It will look similar to this, right?
Yeah.
Yes, ma'am.
Okay. And if n is odd, then how it will look like? It will look similar to x cube graph. Right?
It look like a monotonically increasing or decreasing.
Yeah, so it will approximately look something like this.
Got
Okay.
it.
Yeah.
Thank you, ma'am.
All right.
So it will be monotonically increasing and decreasing. Like the x cube graph, when the power is odd, it is monotonically increasing only now.
Increasing, yes. The slope is always non-negative. Okay. All right. So then we are looking at what are tangent lines. So a tangent line to a curve at a given point is a straight line that just touches the curve. This is what is usually told in your school days, right? Without crossing it. Okay, and has the same slope as the curve. Okay, but usually this is not the definition we are going to look in this course. We will use some limiting definitions for understanding this tangent definition. Okay, fine. So if you are looking at this graph and what is the tangent at this point? Yeah, this is the tangent line. Okay, fine. This is the first basic thing you should know about a tangent, but this is not enough for our level of course. Okay.
Is there any formula to find the point of contact of the tangent at that point of contact, ma'am? To find the point?
Yeah, what is the tangent at this particular point we are talking? So we are talking about what is that point only. Only if we know the point, then we can talk about the tangent at that point. Okay. So you have to know what is this to talk about the tangent at that point. All right.
Is that the derivative of that point, ma'am?
Sorry, what?
Is that the derivative of that point, ma'am?
Yes, yes. So yeah, slowly maybe we'll look into that, but we have not went to that immediately. Slowly we'll see. Yeah, it's the day you have to use the limit formula, which turns out to be the derivative. Maybe in week 8, you will see that, I guess, because in week 7 we are just introducing continuity, and in week 8 you will look at derivatives. Okay. Okay. So I guess you all know this, just a quick recall. In trigonometric functions you have, so maybe instead of a base, sometimes it's also, when you are talking about sine cos, we also call it opposite instead of base. Usually we say opposite, right? Opposite, oh, not opposite, adjacent. This is adjacent, the other one is opposite. So we call this as adjacent and this is opposite because your angle is here. So this is the side opposite to the angle and this is the adjacent side, right? So sine is opposite
by hypotenuse.
And as cos is adjacent by hypotenuse and tan is opposite by adjacent, right? So we have so many other trigonometric functions which are reciprocals of this, right? And we know that all of them are periodic functions, and sine and cos are bounded in the range of -1 to 1. So these are some basic things we should know about trigonometric functions, right? So here you see that this is the graph of sine x, this is the graph of cos x. And for sine x, you see that for sine x as well as cos x, we see that the maximum value it takes is 1. It cannot go beyond this. Similarly, the minimum value it takes is -1 and it cannot go below this. Same is observed for cos x as well. Okay. It is periodic in the sense that, so imagine you just cut out this part, okay, and then paste it again and again, you will get the entire sin x. Same thing for cos x also. If you just cut this part and paste it repeatedly again and again, you will get the entire cos x. These are periodic functions. It means what? If you know what is the function in a given period, so here they are 2 pi periodic. So if you know the function in any 2 pi range, so here you see this is -2 pi to 0 is the 2 pi interval. So if you know the function for any interval of length 2 pi, then you know what is the function for the entire R. So such functions are called periodic functions. Okay. So cos and sine, you know, they are 2 pi periodic. Okay. Similarly, tan. Okay. But here one thing very important is that tan is not defined for all points. Okay. So tan is not defined particularly when pi x is pi by 2 plus n pi. So in each of these points, your tan is not defined. Why? At those points, your cos becomes 0. Since the cos value is becoming 0 and tan is signed by cos, you see that tan is not defined at those points. Okay, so this is about the domain, and about the range, you see that sine and cos are bounded functions. Within this bound, all the values lie. But tan is not a bounded function. You see the value keep on increasing and decreasing. Okay, so they are not, tan is not bounded. Okay.
Ma'am, tan is not defined at what?
These points.
Pi by 2.
Pi by
Pi
2,
by 2.
then pi. At all these points, tan is not defined. Okay. All right. So these are some trigonometric identities which you might use for solving some problems. Okay. So you have to remember them. I guess you already know about composition of functions and what is the domain of composition functions. So how do you compose two functions? And how do you find the range and domain? Do we have any problems for that? No. But I guess you have done this in any of your earlier weeks, right? I remember you have done this earlier, right? Okay, so let's not go much into this because this is already done. Okay. So the definition of graph of a function goes in this way. Graph of a function is the set of all x comma f of x such that x is in x. And this is a subset of x cross y. Okay. So we are just looking at all such points in R2, that is a plane. So we see that graph is given by this. Okay. For example, if you take f of x equal to x square, then all the points x comma x squared in the plane xy, that is your graph. So similarly, sine x, you know that this is the graph, right? This is x comma x sine x. Each of this point is x comma sine x. So this is the graph of sine x. So yeah, so now tangent. How are we defining? The tangent line to a curve C at a point P on C is a line which represents the instantaneous direction in which the curve C moves at that point P. Okay. So now, for example, you take this curve. At this point, you see, this is the tangent. And here, if you take this, at this point, this is the tangent. And for this circle, this is the tangent. So what's the instantaneous direction in which the curve C moves at that point? Okay. So now here for this point, from this line, can you say in which direction can it move? So the graph is actually like this, but when your tangent is like this kind of tangent is not in alignment with the graph structure, you can see, right? So here, particularly these things, we don't even call them as tangents. Only this we call them tangents. But later on, when you look at definition of tangent, you will understand. If it is exactly parallel to your y-axis, you usually don't call them as tangents. Okay. Later on, you can see that as well.
Ma'am, why? Because the slope is infinite. The slope becomes
Exactly.
infinite.
Exactly.
Is it why?
Yeah, exactly. Because the slope is infinite. Yeah.
Circle has infinite tangents, ma'am.
No, we will not have. That's what I'm saying. So if you have a line which has infinite slope, then that does not count as a tangent. We say that the tangent does not exist at those points. Okay.
For the circle, the number of tangents, what I'm talking is the number of tangents are infinite. So because in each and every point, there is a possibility of we can get a tangent, no ma'am?
Exactly. So for any continuous curve on a continuous domain, you have infinitely many tangents because you have infinitely many points.
Yes.
Fine.
At one point, there can be only one tangent, na?
Yes, yes. Okay,
We
all
cannot
these.
have more than one.
Yeah, we cannot have more than one tangent at a point. So at all these lines are tangents to the curves at the point P. In the first curve, we see that a line can be a tangent to the curve at one point and can cut the curve at some other point as well. Okay, so this is possible. Okay. So for example, you look at this step function. Okay, in the case of step function, I have already told you Suppose you want to draw the tangent at the point x is equal to 2. How can we draw? In this case, what is that we need to know? We need to also note that what is limit x goes to 2 plus, and so 2 plus means x to 2 from right. Okay, this is the meaning of 2 plus. What is the value of f of x as x goes to 2 plus? So from the right, where it is approaching?
Towards 3.
It is approaching. What is the y value you have to look? Remember, always when you are talking about limits, we are looking at f of x, that is y value. So the value is 2. Okay. But what is limit x goes to 2 minus, that is from left?
That will become 1, ma'am.
Yeah. So from left, f of x, you see that we are now coming from left, means this is the point you are approaching, which is indicating 1. So it means you are approaching 1. So you see that they are not equal. So in that case, at this point, the limit, the tangent does not exist. Okay. So this is one scenario where you can see that the tangent does not exist. What is the other scenario? The other scenario is some place where we have a sharp corner like this. Whenever you are having a sharp point or sharp edge, in such scenario, you can see that what is the change of direction is not very clear. So in that case also, you cannot have a tangent. Okay. So for y equal to mod x, the tangent at x equal to 0 does not exist, since there are two instantaneous direction existing at x is equal to 0. So at x is equal to 0, either the person can just you can put the direction in this way or this way, right? So and hence we are saying that the tangent does not exist in this case. Okay. So this is yes.
And you said that slope for lines parallel to the y-axis cannot exist. Can it
Yes.
also be horizontal lines now, which are
That
parallel
is,
to the...
yeah, that is possible. Parallel to x-axis is fine because their slope is 0. That is fine. Infinite slope only is not defined. Okay.
Slope
Ma'am,
exists, ma'am, in a greatest integer function.
Yeah, what happens here? What's your question?
Slope exists in this function.
Only at the integer values, it, I guess in the next slide it is mentioned, or next slide. So you see that tangents for this function at integer values, tangent does not exist. Sorry for writing it up and down. Does not exist at integer values. Okay, so whenever you have an integer, you see that the limit does not exist and hence you don't have tangent. But otherwise, suppose you take this or this, there's any such points, they have tangents. Otherwise, it does not have a tangent. Okay.
ma'am, this sign tau, is it the sign
Okay.
tau? Tau, this sign, is it for tangent? This tau sign?
No. This is the this is representing this function, this floor
Okay.
function.
Okay. No, I thought there is one kind of a symbol tau which represent
No.
kind of a
This
tangent.
is not for tangent. This is about this particular function. This is
Okay.
the floor function.
Ma'am, in the sharp edge example, the slope is also 0, no, ma'am.
What is 0?
The slope at that sharp edge point, ma'am. The slope is 0, no, ma'am.
Limit.
No, ma'am. I mean, the tangent is 0, no, ma'am.
There is no tangent. No tangent.
And it will be a horizontal line parallel to the x-axis, no, ma'am. So
No. It is not a horizontal line parallel to x-axis. No. Tangent does not exist. See here,
Ma'am, if there is a
if there is a tangent, then either it should be something like this or something like this. So since we cannot have two such things at a point, then we say that we don't have any tangent at this place. Okay.
ma'am, if the tangent don't exist, suppose at this graph, particularly of mod x, at x is equal to 0, the tangent don't exist. So we can also say that here the differentiation, we cannot differentiate it in a way.
Yes.
But
Yeah.
ma'am, here the limit exists, na? The
Yes.
left hand limit is equal to right hand limit. So limit exists here.
See, the process goes like this. So limit and then continuity and then differentiability. So limit can exist, but continuity need not be. Continuity can be there, but differentiability need not be. But this way, everything will work. If it is differentiable, it is going to be continuous and it is going to, the limit is going to exist. Okay. So it's kind of circles like this. You can clearly see that differentiability is the bigger circle. Sorry for such a poor picture. So the bigger picture. Like, we have not yet come to that point where I can explain everything. So just
Actually, ma'am, in
because.
the TA session, this topic got a little touched. That's why I thought of asking it. In the TA
Okay.
session.
Okay, fine. So since you asked, I'm just hinting what's going on. That's all.
You mention like for any integer value in the step function, there does not exist a tangent.
Yeah.
Right. But
Yeah.
if it's not integer, then you said there can exist a tangent.
Yes.
But don't you think like it will intersect that the line from 1 to 2? So how can any intersecting line how can it be a tangent?
What? Sorry?
Say from 1 to 2, okay, there does not exist a tangent if we draw from 2 or from 1, right? But if we take any point between 1 and 2, let's say 1.5,
Yeah.
so if we draw a line from that intersecting that, so can it be a tangent? How? I'm just confused on that part.
Okay, so you are asking, so we are having, this is the
step function.
Yeah, I understand. So you are having, this is the function you are having. So you are saying, and we are considering one particular point here, let's say this point. So what is the tangent at this point? The tangent at this point is simply this line. So here it is 1, right? So this is the tangent at this point. So in fact, for all x within open interval 1, 2, so x is equal to, y is equal to 1 is the tangent.
Okay.
In the same fashion, every straight line will have a tangent, ma'am.
Sorry, what?
In the same fashion, every straight line, every linear equation or every straight line will have a tangent?
Yes, except the vertical line.
Okay. But this won't hold true in the extreme point of that line, of the
Yes,
segment.
that's why I put open interval. At 1 and 2, we don't have. See, why we don't have at integer values? Because see, we are talking about instantaneous direction. So when I am looking at 2, so I am seeing that the instantaneous direction it move along is I expect that it will continue like this. And here I am expecting it will continue like this. There is no one unique way in which I can decide the direction, and hence I am saying that there is no tangent.
It has hindered the growth of the tangent. That's why.
Oh. All right. So,
Ma'am, when you were saying that if if limit exists, there is a continuity. So ma'am, it's like
no, see,
if limit exists.
Hold on. If limit exists, then only we can talk about continuity. This does not imply. So this does not imply continuity. So it's like steps. I can say step 1, step 2, step 1, step 2, step 3. So they are not like implications. The implication is only in this way. This way we don't have implication. So if limit exists, then we can check for continuity. If limit does not exist, then we can say straight away that it is not continuous and not differentiable. Okay. So for example, this is actually the limit will exist. The function is continuous, but it is not differentiable at x is equal to 0 because the tangent does not exist here. Okay. Fine. I have not yet
But ma'am,
went.
if the function is differentiable, we can say that it is continuous and it
Yes.
is limit exists.
Exactly.
Okay.
Yeah. Okay.
Could you please share this PDF, ma'am?
Yes. Okay. So limit of sequence, convergence sequence, we have seen some examples. So maybe in the next session, we will start with limits of functions. Okay, this is a interesting topic, limits of functions using graphs. Understanding this is a really interesting part. So we'll continue that in the next session, most probably on Tuesday.
Ma'am, where
Ma'am,
I
will
can
you be
find
taking the
the
next session for
previous,
the?
Sorry, what?
where I can find the previous lectures and the previous PDF of these live sessions?
Please ask your friends. I'm not very familiar about where you can find it. So someone can with them.
Are you going to upload this PDF?
Ma'am,
Yes,
can you share right now itself in the chat, madam?
yes, that's what I'm going to do. Just give me a moment. I will
Please,
stop
please.
the sharing part.
Ma'am, can you just go to the section
One
where, what we call
Which one?
Pythagoras?
If any of
The
you guys have the link for the previous session, if you can share it.
Which this one?
Pythagoras right angle triangle part.
Which one? Sorry.
Just go to right angle triangle part.
Okay, yeah.
And the sec x, there is sec not. Just edit the cosec.
Reciprocals.
Yeah.
Yeah, edit the text.
Oh, okay. This was not prepared by me anyway. Okay, fine. Yeah. Okay, thank you.
Is the
Thank
tangent
you.
line define the behavior of the point with respect to that variable, ma'am?
Sorry, what?
On the tangent line,
Yeah.
will it determine the behavior of that function at that point with respect to the one?
Yes, tangent will help you only to understand the behavior at that point. Yeah. Okay.
Does that depend on the variable, ma'am?
Variable does not have to do anything with this. If I put x or y, does not matter. The tangent is going to be the same.
One or two variables in that manner, ma'am.
Sorry, what?
In one or two variables in that manner, ma'am. Does the behavior depend on the number of variables the function depends on, ma'am?
Okay, so if it is a single variable function or multivariable function, is that what you are asking?
Yes, ma'am. Yes, ma'am.
Okay, so in the case of multivariable functions, so we cannot visualize beyond 3D, right? So even for one variable function, the graph you are representing in 2D, right? So if you are having a two variable function, then you can represent the graph in 3D, but we cannot imagine more than that, right? So in 2D, instead of a tangent line, you will have a tangent plane. Okay, so things will get like the dimension will increase. Okay.
So there will be a tangential
You
plane
don't
in
have
2D, you
to,
are saying.
sorry, let me complete this statement. So you don't have to be in a hurry, but if you are interested, definitely you can go and look for it. You are going to see this concept of tangent planes and all in math 2. Yes, the other question, yes. Someone was asking. I stopped you, sorry.
Ma'am, actually in the next, the last PDF that you were sharing,
Yeah.
the last one
Yeah.
when you just started it, yeah. There was one graph of it. Yeah.
1 minute. This page is not flowing. I don't know how. Hold a minute, 1 minute. Hold on. I'm having something
One
hiding.
last question, ma'am.
I'm just struggling to move
Can I
this.
ask a question?
Yeah, just a minute. Let me complete this student's question. We have to just wait. Okay, now it went away.
Okay.
Yes. What was the doubt?
Yeah, ma'am, the first question that you took here, the first question, just in the beginning,
Yeah.
there was one yeah, the fourth one here when you put the graph, you said there's a hole in 3. Yeah, ma'am.
Yes.
Yeah, ma'am. So here the limit exists, but
Yes.
it is the tangent doesn't exist here, na, ma'am.
The tangent here we are talking about the tangent at this point. Yes, it does not exist because function is not continuous here.
Okay. Okay. So we can say that if the LHL is equal to RHL, limit exists.
See,
Yes,
first of
ma'am.
all, limit needs to be exist, and then the function should be defined. The function should be continuous. Then only we can talk about differentiability.
Yeah, ma'am. But in between, what about if the function is continuous, then we can say that the tangent exists.
Yes. Linear functions,
Because
polynomials are
because we took the analogy between three things. The limits, if the limit exists, then continuous, then the continuability, and then differentiability. But what about the tangent thing in between these three things? If it is continuous,
differentiability
then the
and
tangent.
hold on. Differentiability and existence of tangents are same.
Okay, ma'am. Okay. Thank you.
Yes. Any maybe
Ma'am, I
just
had
one
one
last
doubt.
question. Yes.
Ma'am, one question of the PYQ. Ma'am, will I speak the question or I will share the screen?
Oh, if you are asking about one specific question, maybe we'll do it in the doubt session on Tuesday. Okay,
No,
because
ma'am,
we have
just one thing. Just
Ma'am,
I can say just like there is one function of fx like x.
hold on. See, I'll maybe first address questions which are concerning the topics discussed today. Are there any questions? One last question. Please, sorry, I'm not
ma'am,
getting you. Maybe in the next session, some new things we will see. Yeah, sorry. Yeah. What's the other?
I have a question. Can you please explain about convergence and divergence?
That's what I was explaining in the beginning, I guess. See, convergence and divergence, if you want to understand, just a simple example I will tell you. So, as I told you, the first example I told is about 1 by n or 1 by x, right? So, what happens to this function? You see that what is happening? This function, as x goes to infinity, it is not approaching any single value. So in this case, the function as x goes to 0, 1 by x does not converge. So this is one scenario. Okay, similarly, if you have the step function, so in the case of step functions also, you see that suppose I am saying this is 1. So as x goes to 1 plus and x goes to 1 minus, the limit of the functions are not equal. So here the function is not converging as x goes to 1, the function is not converging to any specific point. And converging means it is approaching one fixed point. Either you look from the left or right. If it is coming to one particular point, then we say it is convergent. So if you are taking any other functions, smooth functions, so if you are taking any other functions like this, so at this point, if you are talking about the continuity at this point or the convergence, you see that either from the left or right, it is converging to the same point. Okay, so this is about convergence and divergence. Okay, all right. Okay, so thank you everyone. I hope this session was useful. I will be sharing the notes right now. Please wait for a minute.
Okay, thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you everyone.
And when will be the next session, ma'am?
I guess it's on Tuesday.
Ma'am, please convert the uncovered part also, ma'am. Why? Because lot of definitions are there, formulas, so that we can have a look.
It will be covered. It will be covered.
Okay.
Mhm.
Ma'am, there is no session mentioned on Tuesday in the calendar, ma'am. So will we
Sorry.
get the link? And there is no session mentioned on Tuesday in the calendar, ma'am.
I guess it will be updated. Okay.
Okay. Yes, ma'am. Sure.
Okay, week 7. Okay, I have shared both the PDFs here. Okay, fine.
Yes, ma'am.
Okay, so thank you, everyone.
Thank you, ma'am. Thank you very much.
Yeah.
In the next session, you will be taking or the other teacher?
I guess the next session will be done by, I don't know, either Vishal or Abhilasha. I'm not sure.
Guys, anyone of you have the previous notes of PDF?